This is the first in a series of videos about equilibrium calculations. We have spent the last few videos talking qualitatively about equilibrium, which direction does it move, and now we need to talk about how much does it move, and we're going to talk about how to calculate that and how the stoichiometry of the system is related to it. We'll use ice tables and do a series of examples, and then we'll add in a super fun fact relating the equilibrium constant back to our Gibbs free energy from thermodynamics. So it is time to talk about quantitative equilibrium. So we can calculate how much each concentration shifts, which is what we've been talking about all along. And we need two things to do that. First thing that we need is a balanced equation. Because we need the coefficients that go in front of each of the different compounds. And the second thing we need is our equilibrium constant. And that's K. So let's look at that first item at the beginning. So the balanced equation, we need the coefficients, and the coefficients come from the stoichiometry of the shift. Stoichiometry is a fancy word for the reaction coefficients. So the shift that's felt by each substance is going to be related to the stoichiometry. And we know this in our hearts already when we learn to balance reactions and to use them in thermodynamics. So stoichiometry means coefficients. So we know in our hearts already that those coefficients are important, that when we have two of one thing, we may have one of another or three of another. So let's talk about how the shift works. Are there a shift towards the right or a shift towards the left for different reactions, and look at how the stoichiometry is related. So here's what we're going to do. We're going to do our generic reaction first with reactants going to products. And we are going to look at the shift direction and what happens. So in this case, we are shifting to the right. Put a box around that. And when we shift to the right, we said that the reactant amount decreases and the product amount increases. So there's going to be a decrease, there's going to be a minus sign, and increases is going to be a plus sign, and we don't know how much, but we know the relationship is going to be 1-to-1 because of the coefficients, so we'll just write X for both of them. Okay, let's do the same thing over here for a shift to the left. Shift, there's our line. Okay, when we shift to the left, we decrease the amount of products and we increase the amount of reactants, and we increase it and decrease it by the coefficients, which are both 1 in this case. Okay, so far so good. For the generic reaction, let's move on to a real reaction with real chemical compounds. Let's do N2O4 gas goes to 2 nitrogen dioxide gas. Okay. So if we're going to shift to the right, we're going to subtract from the reactant side and add to the product side, but this time we have non-1 coefficients. One of these is a 1 and one of these is a 2. So we know that the side with the 2 on it is going to shift by twice as much as the side with the 1. So we're going to subtract 1 times X and we're going to add 2 times X. Oops, almost forgot the 2. There we go. Okay, same deal over here. If we shift to the left, we're subtracting the products, we're adding to the reactants, and then we're going to use our coefficients from stoichiometry, subtracting 2 equivalents on this side and 1 equivalent on this side. Okay, you should be starting to see a pattern of how this works. Not so bad. Just want to break it down and make sure that each step is clear. So I forgot my state symbols here. Gas, liquid, aqueous, aqueous. All right, here's a preview into the next chapter. HCl plus water goes to H3O plus Cl minus. So if we're shifting to the right, we are going to subtract each of the things on the left side, and we are going to add each of the things on the right side. So in this case, we have more than one reactant and more than one product, but we can still go ahead and add both of them. You'll notice that I didn't put a minus sign under the water, and remember that's because water as a liquid, that is a pure solid or liquid, and we don't include those. We'll put a little asterisk here. Remember that pure solids and liquids are not included. They're not included in the K, and they're not included here when we think about the shift, because they don't shift enough to matter. The concentration of a pure liquid or a pure solid is so little compared to how much is present that it isn't really relevant. So just to remind myself that I'm not going to use this in the table, I'm going to put a squiggle under the water. And then all my stoichiometric coefficients are 1. So it's just going to be 1x for each of these for the shift. Okay, we'll see if we can fit this one in here for the left shift. Aqueous and aqueous. I'm putting a line here just to separate the reactants from the products. Okay, so this time we're shifting towards the left. So we're going to subtract our products, we're going to add our reactants, and we're not going to include water because it's a pure liquid. And there's a 1 in front of each of them, plus 1, minus 1, minus 1x. So all we're doing is we're using those stoichiometric numbers that are in front of the balanced compound, and we're using that to tell us how much that side is going to change. And then we're using the shift direction to tell us whether we're going to be subtracting or adding. So this has been our preparation leading up to how to use our new tool, the ice table. So in the next video, we will talk about how to officially and formally use an ice table to calculate how much the concentration shifts to reach equilibrium.